My name's Ethan Rhodes, and today we'll be going over the results of our 2D airfoil lab. I'm going to be going over the introduction. Understanding two-dimensional airfoil theory is important because it allows for ease in design to achieve the proper lift while minimizing the drag, which is the typical goal of an airfoil. Having a low drag coefficients is also important, as you want to be as fuel efficient as possible and get the most out of your lift. And 2D airfoil theory helps demonstrate the behaviors in broader terms, so you can look at what would happen at different Reynolds numbers along with the varying angles of attack of your airfoil. We tested an S-08 airfoil, which is mainly used for wind turbines. It's designed to maintain constant low drag throughout varying angles of attack. We tested a Reynolds number of 700,000. The primary objectives of our lab was to generate pressure distribution plots, calculate lift coefficients, calculate drag coefficients for our angles of attack of -14 degrees and +5 degrees. And then we used other teams' data to produce the coefficient of lift versus angle of attack, coefficient of drag versus angle of attack, coefficient of lift versus coefficient of drag, and the coefficient ratios versus many angles of attack. And I will be passing it on to Joe to do the theory of the lab.
Yep. So I'm Joe D'Imperio. I'm going to talk about the theory behind our experiment and the equations we use to get our data. So as you can see here, we're examining a two-dimensional airfoil. Some important things to note are the normal force coming directly perpendicular to the camber line of the airfoil, the velocity coming, the free stream velocity coming in, drag coming in the same parallel to the free stream velocity. And some important things we're going to look at are the drag on the airfoil and the lift generated by the free stream velocity that the airfoil is experiencing. So the first step was to look at the pressure coefficients across the surface of our airfoil. We have to separate the upper and lower surfaces of the airfoil and look at individual points across each surface of the airfoil. So each equation here represents an individual point on either the upper or lower surface. And as you can see, into the calculation, we have to look at things from our actual experiment. So SG here represents specific gravity, which in the case of our experiment would have been alcohol in our manometer tubes. And sine theta m represents the bank angle of our manometer device, so that whatever bank angle we use for the manometer is taken into account in our final calculations and is still concurrent with our theory. We then have our readings here where we're comparing free stream velocity, free stream pressures versus the actual pressure experienced on these individual points on the airfoil. So now that we have these individual components of our pressure coefficients, we can bring them in to find a coefficient for the normal force that actually generates lift. So this is done in a mesh numerical methods manner, where we actually have to look at the series and integrate over the entire surface of our airfoil, where we calculate for each pressure coefficient coming together and to form the single normal coefficient on our airfoil. So into this normal coefficient, it's important to note that if it is positive, that means we have positive lift, and that in order for it to be positive, we have to have a lower pressure coefficients across the upper surface of our airfoil as opposed to the lower surface to generate this lift. And it is important also to note that the angle of attack comes into account here as well, so that it's not just the normal coefficient, but the normal coefficient by the cosine of our angle of attack that actually generates the lift. So in order to calculate the drag coefficients on our airfoil, we have to use Simpson's rule. Simpson's rule is an integration of the wake profile experienced behind the airfoil. So the first equation we want to look at here is the F of Y equation, which is looking at individual points in the wake of the airfoil, looking at the dynamic pressure in that local area, as opposed to the dynamic pressures at the beginnings of the wake, and seeing the difference there. And then we integrate that across over the entire surface of the airfoil, or entire core of the airfoil, for each upper and lower surface. And we use this step H, which, as you can see here, it has to, for Simpson's rule, we need to have an even number of steps, and we integrate from the beginning to end of the chord, where we look at the number of steps necessary, which gives us our step over the chord H. So all these integrations of Simpson's rule then come into our coefficient of drag, which is simply calculated here by taking each of these integrations into these values S, which are then multiplied into our coefficient of drag calculation. So now I'm going to turn it over to my partner Connor, who is going to discuss the lab setup and procedure.
I'm Connor Keith. I'll be going over the lab setup and procedure. So, our lab setup was designed to measure the pressure distribution across the airfoil at 5 degrees and negative 14 degrees. This was to give us a feeling of how the airfoil will perform at angle of attack. So to do that, we used a manometer bank, which was tilted at 61.4 degrees and 85.3 degrees, where a higher angle of tilt would result in a lower resolution, and a lower angle would result in a higher resolution. So this is a chart measuring the channels used in the manometer bank, where channels 1 through 17 were used to measure the upper surface of the airfoil. Channel 18 was used to measure the atmospheric pressure. Channel 19 was used to measure the static pressure in the wind tunnel, and channels 23 through 36 would measure the static pressure at the bottom of the airfoil. So our hot wire was calibrated so the delta P at 1.6 volts would result in a Reynolds number of 700,000, which was the goal for our initial condition of the experiment. So the traverse was used to measure the velocity across the height of the airfoil, so that we could create a graph of the velocity after the airfoil. And now Jake will be going over the results.
Hi, I'm Jake Perzak. I'm going to be discussing the results of the experiment that we found from the 2D wind tunnel testing. So the first thing we were tasked with finding was the velocity distribution behind the airfoil as a function of the height in the wind tunnel. As Connor mentioned, this is why we're using the hot wire anemometer to measure the velocity of the air after it passed over the wind tunnel. We use an angle of attack of 5 degrees and 14 degrees. As these graphs show, at a higher angle of attack, when the airfoil is essentially taking up more space within the wind tunnel, the velocity drop is taking over a higher air than it would at a lower angle of attack, because like I was saying, being at a lower angle of attack is affecting less of the velocity, therefore resulting in less of a drop downwind of the airfoil. Another thing we needed to find was the coefficient of pressure distribution, or how it was distributed over the airfoil. Based on the camber of the airfoil that we had, where the camber is highest is where the pressure would also be the biggest difference from the lower and the upper surface. This is at negative 14 degrees, and this is at an angle of attack of 5 degrees. And again, as these graphs show, the higher differences in the pressure distribution is resulting over the camber. And as we've learned from classes, the lower pressure on the top is favorable and a higher pressure on the bottom, and that's what's helping create lift on the airfoil. Here is a graph of the actual coefficient of lift versus angle of attack and how it's changing from different angles of attack. This data was found with all 16 groups, or all groups and their 16 data points. As this is showing, as angle of attack increases, the coefficient of lift is increasing. This is because with an increase of angle of attack, the velocity over the airfoil is increasing, and therefore it's resulting in a higher lift. However, as the graph kind of dips down, that's where the airfoil is stalling because the boundary layer is separating very, very close to the leading edge, and therefore it's unable to produce any lift. This is pretty accurate and concurrent with what we were expecting to find, as like what was given in the assignment sheet. It increases linearly with angle of attack and then decreases around the stalling point of the airfoil. We also graphed the coefficient of lift versus the coefficient of drag, resulting in a horizontal bucket. Again, this was with all the data points from the given angles of attack for all of the groups. The trend that we found was very similar to what we were expecting, as was given in the assignment sheet. There were slight discrepancies in the data towards the latter half, or towards the higher angles of attack, but that's just because of some errors that could have happened as a result of this experiment, which Luke is going to be going over after me. Also, we graphed the coefficient of drag as a function of angle of attack. This graph is pretty similar to what was expected. This wasn't actually a given graph. This was an extra credit portion for this assignment. So this graph was actually compared with a graph taken from Google Images. Note how large the bucket of the graph is. This is good because we want low coefficient of drag at low angles of attack. This is between about -6 degrees and +6 degrees, which is more or less what the airfoil is going to be experiencing at steady level flight. So it's important that it's very wide at these low angles of attack. The axes are also slightly off in terms of the actual numbers, but we decided to go with a factor of 1,000 just to make the data more presentable. Finally, we graphed the coefficient of lift over coefficient of drag as a function of angle of attack. Again, this was an extra credit portion of the assignment, and so there was no given graph to compare it to, so we used one from Google Images to compare. But as this is showing at intermediate angles of attack, the coefficient of lift over coefficient of drag ratio is the highest. It's occurring around approximately 8 degrees angle of attack, maybe in that 8 to 10 range, which is expected for this airfoil as well. That's all we had for the results of the experiment. As I mentioned, some of the errors. We're going to go over that a little bit more in the conclusion section with my next partner, Luke.
Hi, my name is Luke Baer, and we'll be going over the conclusion of this lab experiment. And so, to conclude, this lab was basically a capstone of our entire aerospace portion of the laboratory section. And by being a capstone, we had to, in earlier labs, set up to this one. And that includes calibrating the venturi factor of the wind tunnel that we had, calibrating the transducer, the pressure transducer, which would convert our pressure to speed in the wind tunnel. And then we also had to calculate or calibrate the hot wire, which would give us the velocity down towards the finishing portion of the wind tunnel. And putting all that together, we were then able to determine the pressure all over the airfoil that was tested in this experiment, and then calibrate, and along with all those calibrations from before, we were able to put all those together and then plot the lift and drag coefficients for that airfoil and come up with the plots that you saw in the results section with Jake. So some of the errors that you may see in our data is because all the data was collected by different sections of this lab group, and different sections of the lab may have conducted their experiment a little bit differently, which may have yielded slightly different quantities for the results. And so putting all those together is going to result in just tiny differences in our plots. Also, maintaining the Reynolds number during our test. So all of our tests, our Reynolds number, our ideal Reynolds number was about 700,000, and in order to maintain that number, we had to maintain a constant speed in the wind tunnel. And in order to maintain a constant speed, someone had to control the dial, which would then in turn read off the pressure transducer, which would give us a voltage that we wanted that to remain constant. And it was a very hard job for that person to do. And so although it was human error, it's also almost impossible to maintain a completely constant speed in the wind tunnel. But overall, our results compared, as seen in the results section with Jake, the results compared very well to external data that we found on the internet by other sources. And so our experiment conducted by the other groups, put all together, yielded very good results for all of us.